In this video, I will briefly go through the notes on objects, interactions, and forces that we did in class this week, in week 3. So we started out, each person had a washer and a rubber band, and we held them like this, so the same way it shows on the diagram. And we talked about, do you think there's forces occurring here? And it seems that there is a force on the washer from the rubber band, and probably from the hand on the washer. And we started out then with a definition that objects are interacting if they are touching, or if they are affecting each other at a distance gravitationally, magnetically, or electrically. So when we work with forces and interactions, we always want to diagram what objects are interacting. And so the objects here that seem to be important for the washer is our object of interest, are the hand, the washer, and the rubber band. So you write the name of each object that you think is important and put an oval around it. Then, to show which objects are interacting, we want to draw a line connecting the names of the objects that are interacting. So they're interacting if they are touching. So we have a hand touching the washer. So that tells me there's an interaction between the hand and the washer. And the rubber band is touching the washer, so there's also an interaction between the rubber band and the washer. Now, you could extend this and include the other hand that's touching the rubber band. So, this diagram, and then of course your body is connected to your hand and your body's touching the floor. So you can go on, but because it's the washer that we're interested in, these are the only objects we need to include. Now, there is gravity, so the earth is also interacting, but for now, for this example, to keep it simple, we're going to leave that out. So we've defined what an interaction is. Next, we're going to talk about a force. A force is a push or pull that results from an interaction between two objects. So this is an interaction, and as a result of that interaction, there is a force of the rubber band on the washer. But there's also a force of the washer on the rubber band. So each interaction results in two forces, one on each object. And here's an example. The interaction between the washer and my hand results in these forces. The force of the washer on my hand. Okay, so that is the force of the washer on my hand, and the force of the hand on the washer. Okay, so you kind of like both ends of that interaction line represent a force. Each force has a magnitude and a direction. So if you think back to the rubber band here, I can make it longer and pull on it, right? You know that that's increasing the strength of the force. It's going to hurt more if I let go. And then I can also change the direction of that force. It can be represented by drawing an arrow. An arrow is really great for representing things that have a magnitude or like a strength and a direction, because the way the arrow points shows us the direction, and then the length of the arrow represents the magnitude. And we have names for these parts of the arrow. This is the tip, and this is the tail. Sometimes when there is more than one force pushing or pulling on an object, the forces cancel each other out. When this happens, we say the forces are balanced. If you add up the forces, the sum of the forces will be 0. And let's take a look at another diagram now that we can draw for forces. This diagram right here is called a system schema diagram. And the next diagram we're going to draw is going to be called a free body diagram. and often we will just abbreviate that as FBD. Now in a free body diagram, what we want to analyze is all of the forces on just a single object. So we have 3 objects here involved in our situation, but we want to analyze just the forces on one of them. I'm going to choose that I want to analyze the forces on the washer. So I put a dotted line around it to show that that's the object I'm going to analyze. And on the free body diagram, what you do is you represent that object with a dot. So this dot is representing the washer. So we've really simplified it, right? It used to have this shape. Now we're just going to say, let's consider it to be a point object, and let's draw only the forces on that one object. Now the usefulness of the system schema diagram is that each interaction line that crosses this boundary represents a force. So you can easily see that since there are 2 lines that cross that boundary, there are 2 forces on the washer. And we're going to represent each of those forces with an arrow. So let's do the rubber band first. The rubber band is pulling to the right. So we draw an arrow to the right. And we will label that with each of the objects that were involved here. So this is the force of the rubber band on the washer. Okay, now there's another force. There's the force of the hand on the washer. We want to draw that one too. And I know it's going to be to the left because the hand is pulling to the left, but how long should I draw it? So here's the question. Are these forces the same strength or not? And I'm going to try to demonstrate this. And it's not possible for me to find 2 rubber bands that are exactly the same. So this demonstration has its limitations. But maybe qualitatively we can see here that since both of these rubber bands are stretched about the same amount, that when the object is at rest, it has equal forces to the right and to the left on it. And let's see, maybe we can get a little bit more precise with this by using a spring scale. So this has a spring inside of it, and when it's stretched, it tells the amount of force that it's pulling with. So we're going to put a spring scale on each side in place of the rubber band. And hopefully this will show on the video. Okay, we have some uncertainty. You can see this thing here, but okay. So let's pull with this. Okay, and hopefully you can see and would agree that there's 3 newtons pulling one way and there's 3 newtons pulling the other way. And so we can see that these forces have the same magnitude but opposite direction. So that tells me that I should draw an arrow this way of the same length. And to show that I mean them to be the same length, we'll use the little congruency marks from math. And then let's label that force. This is the force of the hand on the washer. Next week we'll have some shorter names for forces, but for this week I want you to be writing the names of the objects that are included there. Okay, if an object is at rest, then the forces on the object must be balanced. Okay, this was an object at rest, and we saw that the forces were balanced. It's the same amount pulling this way as is pulling that way. Or if you were going to add these forces up, they would add up to 0 because the direction counts, right? One is positive, the other one's negative. Now, it was easy here to know that these 2 forces had to be the same magnitude because there are only 2 forces and they're opposite. If you have 3 forces on an object, and that object is at rest, these forces are still balanced, but depending on the angles, these may or may not all be the same magnitude. So it's not so easy to deduce an unknown in this situation as it is when there are only 2 and they're opposite.